Hello, my name is Paolo Zannetti. I'm the president of APSI, the Air Pollution Scientific Initiative. And as part of the APSI activities today, with the help of my friend and colleague, Dr. Zafer Boybeyi, we are going to interview Dr. Paul Arya, who is I would say, a founding father in terms of air pollution meteorology and application, air quality applications.
Oh, you should not say founding father. There are other founding fathers.
There are other founding fathers. Okay. I think your seniority is quite impressive, Paul. But certainly you will explain today to us your life and your achievements. So okay. That's what I'm not going to introduce you with a formal list of your accomplishment, but I will let you start and asking about a summary of your professional career.
Okay, I'll start with my beginning. You know, I have very humble beginnings in India. I was born in India, you know, in a small village. My family was a farm family. They had a small farm. And I was brought up on that, and I helped them on the farm too, you know. And after I went to the local school, middle school, high school, you know, I had to walk 3 miles each way every day up to high school. That means up to 10th grade. And then I went to a college where I did my 11th and 12th grade. So here the high school is really 12th grade. In India, they call it intermediate college. So that was about 16 miles from my place, and I lived in a hostel or dormitory. And from there, I went to another college, my district Merit College, and I did my Bachelor of Science, Part 1. And doing that, I actually appeared for an All India competitive exam for engineering at University of Roorkee. University of Roorkee is one of the oldest engineering universities in Asia. It started, of course, by British in 1847 or so. And after 100 years, it became, earlier it was a Thompson College of Engineering, then became the University of Roorkee in 1947, when India became independent.
Yep.
So I entered the university. I was lucky to get into that competitive exam. I was selected to be one of the students in civil engineering because I gave my choice as civil engineering. So I entered in 1958 there after my BSc Part 1. So I went to Roorkee. And it was a 3-year course at that time, and I graduated in 1961 with a degree in bachelor's BE in civil engineering. So I have a kind of started with the bachelor in civil engineering, and after I graduated, I actually went to my provincial government, you know, the capital. I joined as an assistant engineer in their design directorate. So for 1 year, I was involved in the design of tunnels for a hydroelectric project. But I realized that I'll go for further education and maybe get into an academic program. So I came back to Roorkee to do my master's. And so after 1 year, I came back to Roorkee again and enrolled in the master's program. And that was in hydraulics and fluid mechanics, dam design, those kind of fields. And so I did that they call postgraduate diploma for 1 year, and then you write a thesis to get a degree, ME degree, Master of Engineering degree. And in the meantime, after the diploma, they hired me as a lecturer in civil engineering. So I became a lecturer also in civil engineering in 1963. And I taught courses in hydraulics, fluid mechanics, uh, other engineering courses, hydrology and so on. And in the meantime, I also wrote my thesis in, I remember it's a groundwater recharge, groundwater recharge, kind of reviewing the work they had been doing in California, at that time. So I got my bachelor's or master's degree in 1964. And in 65, I applied for assistantship and admission in the U.S. I was given admission at 3 universities, but I accepted at Colorado State University. So I got enrolled in the Fluid Dynamics and Diffusion program of Colorado State University. It was again in the Department of Civil Engineering there, but they had a fluid dynamics and diffusion laboratory, where they had wind tunnels, large wind tunnel. They were doing some experimental work in modeling wind flow around buildings and other simulations using the wind tunnel. They called the Army wind tunnel, and it was supported by U.S. Army. And you could create you can also simulate the atmospheric boundary layer, the thermal stratification. You can heat the floor and cool the air, or cool the floor and heat the air, and create different stratification, stable, neutral, and unstable. So I started working for my PhD dissertation in that wind tunnel while I was taking a number of courses, of course, in fluid mechanics and hydraulics and mathematics and so on. So I finished my degree in 3 years, 1968, got my PhD at that time, and stayed there for another year as a postdoctoral fellow. So I got a postdoctoral fellowship for a year, and I was looking for a job. I applied a number of places, and with my advisor's recommendation, my advisor was Professor Eric Platte. He was from Germany, and he was from University of Karlsruhe, came to the U.S., and actually after I graduated, after 2 years, he went back there, as a professor in University of Karlsruhe. So I visited him a couple of times there. And but I got a job at the University of Washington in the Department of Atmospheric Sciences as a research assistant professor. So I started working there as a research assistant professor under Professor Businger. They had a energy transfer group there, so I was part of the energy transfer group, and we worked in mostly boundary layer processes and turbulence. So not so much in air pollution at that time. Air-sea interaction was one.
Yeah.
And we conducted a few field experiments. Like I remember, I joined in 1969, and in 73, Professor Businger and I took part in a AJAX, an experiment, Arctic Ice Dynamics Joint Experiment. AJAX is called, 1973. It was a preliminary experiment that time before a full-blown experiment later on. But, we went to about 250 miles from the North Pole on the Arctic sea ice, and actually it was, we first went to Naval Research Lab there, on the coast, and they provided us with the appropriate clothing, because it was very cold there. So it was in March, and we went from by plane, transport plane there, and landed. The plane landed on the ice. Ice was strong enough, thick enough to land on the ice, and we had our tents were also flown from the same lab. So there were some 60 scientists, taking part in this. Some meteorologists, some oceanographers, some geophysicists, and it was a nice experience, first experience to be there about a week. I stayed there about a week or so, a week or 10 days, and came back, and we took part in other field experiments on the Great Lakes. It was called IFIGL, International Field Year of Great Lakes. So I took part in that also. Professor Businger and some of his students, and we went there. We had a station south wind of the Lake Ontario near Rochester, and we set up a tower there, making measurement of winds, temperature, fluxes, and so on. So that was a good experience. Idea was to study the lake effect snows, when the cold air outbreaks takes place over warm lake, and then studying there. Some people were actually even flying the aircraft across the lake at that time. So that was a very good experience. And I think there were few local experiments in Puget Sound there, studying air-sea interaction. But I think in 1976, I was looking for a tenure track job, and I found one here at North Carolina State University. So North Carolina State University, it was Department of Geosciences. I was offered an associate professor of meteorology, and so I accepted that. And since then, I have been here at in Raleigh, North Carolina State University. The department later became, I think, after a few years, Department of Marine, Earth, and Atmospheric Sciences. So right now it's the Marine, Earth, and Atmospheric Sciences. We got all three disciplines, and I acted on the interaction. I interacted with marine sciences too, because my interest was also in air-sea interaction. And I taught a number of courses here, like environmental fluid mechanics, air-sea interaction, micrometeorology, planetary boundary layer, atmospheric turbulence, atmospheric diffusion. Most of these were graduate courses, except for micrometeorology, that was undergraduate course, and air pollution meteorology also. It was both senior undergraduates and graduate student could take. It's kind of common to both. And so I had also, of course, applied to number of research grants from National Science Foundation. I was working on an NSF grant at University of Washington, so I continue in that area on boundary layer and turbulence. And moving over here, I took advantage of the fact that U.S. Environmental Protection Agency was located here in the Research Triangle Park, and they had a fluid modeling facility. Since for PhD, I did work in a fluid modeling, in wind tunnels, and I found out that they also had similar facilities here in RTP. So I applied for the grants, or they called cooperative agreements. So they gave cooperative agreements every 3 years or so. And on those cooperative agreements, they supported 3 of my graduate students, and sometimes visiting faculty, you know, from like England. I got Julian Hunt here visiting with us several
Yes.
times.
Yeah.
Yeah,
Julian.
Rex Bilter also came here, stayed for a year, and we had several other visiting scientists on that program. One person from Germany, he came over here too. So I had that cooperative agreement with EPA for more than 20 years uh, until almost near the end of 1998 or 1999.
That's
So
wonderful.
it was a very productive one. We got graduating many students, on that program. And this National Science Foundation grant I had, we had a lot of students, PhD, master's students working on that too. And I got grants from NASA also, studying the aircraft wake vortices and how they affect the following aircraft. They were interested in deciding what should be the minimum spacing between the aircraft,
Ah,
uh, or the maximum safe spacing, between the aircraft. So we studied those aircraft vortices and their interaction with the following aircraft and so on. So that was a very NASA-funded project. Another project was with another professor here. He was studying the agricultural air pollution, Dr. Vinay Aneja. So he was interested in agricultural pollution, like especially related to the hog farms. Our state, North Carolina, a lot of hog farms, and
uh-huh.
they were studying, how the hog farm waste is impacting the surrounding areas. So we did study the emissions of ammonia and pathogens and other odor and so on. So there was a project between our universities, Duke University and UNC Chapel Hill, called Open Odor, Pathogens, and Emissions of Ammonia, that emissions of nitrogen open. So we had that 6 year or more longer project on, we worked on that too. So in a way, yeah, that lasted. And then towards the end, my last project was with funded by uh, yeah, Chesapeake Bay Foundation, CBF.
Hmm.
Dr. Neja and I had a joint project funded by CBF studying the impact of various poultry farms on Chesapeake Bay and how it was impacting the waters of the bay there, of the Chesapeake Bay. Well, how it was affecting the Chesapeake Bay. These poultry farms were on the peninsula. So we studied those, that both experiments and also modeling of the pollutants there.
Okay.
So
Well, thank you for the summary. That's very comprehensive. And I'm going to ask you later about Businger, but let's have Zafer continue with the next question now.
Okay.
Well, you refresh my memories about NC State. Paul. Actually, Paul was my professor at MES, Marine Earth and Atmospheric Science Department, one of my professors, and he served in my PhD committee. I'd like to ask you about your memories of interactions with other important scientists. You mentioned about Businger, for example, that they may not be alive today.
But Businger is still alive. He's there. He retired
yes.
for a long time. Yeah,
it's good to hear. Good to
hear.
Yeah. If you remember, it was, I think, 1992. He came to our department, gave a seminar.
Oh, yeah. Yeah.
which is only using the 3 slides and 1 hour, the lecture type of, the presentation. It was wonderful, actually. I remember that.
We hired his son, Steve Businger, as a faculty member. I think he came when his son was here. Yeah.
Well, just for the memory of all other, the colleagues that you interacted in the past that they may not be with us today, if you want to share some of your experiences with them and some of their breakthrough work, because you've been in this field for a long time, and you're considered one of the, the leading scientists actually in this area. So if you can share your memories, that would be wonderful.
Well, yeah, I think one of the person on my top of my list is Frank Pascal. He's a British scientist. He wrote books, on atmospheric diffusion. I think the earliest part was 1962, then 1974, his second edition. So used they form really textbook for my courses on atmospheric diffusion. And another person who worked with Pascal was also Gifford, Frank Gifford. He was with NOAA and Oak Ridge National Lab. He was there. I visited him there. Pascal, I remember when he visited with the US EPA, we invited him to our house. He came there, and Julian Hunt was there too. So I had good memories of him visiting with us. And Frank Gifford, I remember I met him in Oak Ridge National Lab and a number of other conferences. Certainly, he was one of our leading scientists in this area. Pascal Gifford, stability categories, remember it was that. Another British scientist I remember was George Batchelor. I used his books on fluid dynamics, and there were, of course, Russian scientists like Andrei Yaglom. I met Yaglom also one time here at the University of Washington. And Kolmogorov I met in one of the early meetings in Australia, in Melbourne. He attended that. So the first time I saw Kolmogorov over there. And Deardorff, Jim Deardorff, I remember him very well. He was one of the, I think, the pioneers in numerical modeling, especially he called three-dimensional modeling. Now we call it large AD simulation, LES modeling. So Deardorff started the work in that area. And Gary Briggs, he was a scientist at EPA. He did a lot of work in modeling. Yeah.
Plumrise study, yeah.
Plumrise, yeah.
Plumrise, yeah. And also those categories, stability categories. I think he defined in a different way, then. So I recall some of these scientists.
Very good, very good. The next question, Paul, is probably the most difficult one. Excitements, joys, regrets, frustrations. You had a very long career, so I'm sure you can talk about these things.
Yeah, well, I'm sure the excitements and joys I got mostly from field experiments, taking part in field experiments, meeting other scientists, and kind of working in collaboration with them. Some of the field experiments, like I mentioned, was this AJAX in Arctic, IFIGO over Great Lakes. And when I joined North Carolina State University, we had a large experiment called GALE, Genesis of Atlantic Lows Experiment, GALE. So it studied how the storms moving over the Gulf Stream or east, near the coast, Atlantic coast, how they get intensified and their genesis and how they sometimes can generate hurricanes even. So
I
we
remember that experiment actually. We also took part of that, when I was a student there. Yeah.
yeah, you might be a student at that time. It was in 1986, actually, that
Yeah,
experiment.
there's a lot of analysis of data from that experiment.
Yeah, Dr. Sathu Raman was actually in charge of that experiment in our group,
Right.
but there were other scientists involved too, Peter Hobbs from University of Washington and other scientists,
Yeah.
So we had a large group, again, maybe more than 60 scientists, some flying aircraft, some using their research vessels. I I remember I went on a research vessel, Cape Hatteras, which belonged to Duke University and NC State and UNC together.
I was on that for 3
You were
months.
on that? Oh yeah, yeah.
3 months.
So I had an experience, of course. I
Yeah.
got seasick there for a couple of days. I was down very bad. So that was one of the frustrations, even though it was a very good experience. But a couple of days I was seasick, I couldn't eat or could
Oh
not
yeah, you tell
retain
me
anything.
about that.
Yeah, yeah. And so, and also sometimes, these things happen like in Ajax, the Arctic experiment, we, Bussinger, he designed some sonic anemometers and wanted to use those to measure the stresses and turbulence. And we took them and mounted on a tower, and we didn't realize the effect of the temperature. The temperature there was minus 35 degrees Celsius all the time,
Celsius.
day and night. Yeah. And those cables connecting to the instruments got so stiff that just touching them, kind of they snapped. So, with so much effort, we took those instruments and then those cables got snapped, so we could not use them actually. That was one of the frustrations, and we didn't have any other cables to replace them. Yeah. So those kinds of things do happen. But I don't have any regrets in terms of, that I shouldn't have taken part in this. I always enjoyed these field experiments. Although my personal interest was more in theory and modeling, theory. Well, my PhD research was experimental, simulating the atmospheric boundary layer in a wind tunnel. And that experience actually helped me to get these EPA grants and doing studies of flow and dispersion over hills and around buildings and so on, in complex topography. So complex rain dispersion was studied using those wind tunnel facilities.
Very good. Very good. Thank you for the memories.
Well, next, what I wanted to actually ask you, the air pollution and air quality modeling. Let's just talk about a little bit, the modeling area.
Mm-hmm.
As you know very well, the models are always a simplified version of reality of the system being simulated. So there are always going to be uncertainty in numerical models.
Yeah.
The key question is here, how good is the complex computer models really are for their intended purposes, and what uncertainties involved in their prediction.
Mm-hmm.
And a subsequent question clearly is how to reduce these uncertainties so that, to make the models better,
Yeah.
As an experience, the scientists working in this field, I just wanted to get your views on these issues, the modeling issues, the persistent problems, and looking ahead, actually, where we are today and how we can progress.
Well, as you know, I retired in 2009, so it has been more than 11 years since I retired. But I, you know, I'm surprised. Well, even if I retired, I've been serving on graduate student committees, and actually on some of them they asked me to be their advisor, co-advisor, and one of my PhD, the last PhD student, he's just finishing up his PhD degree. Actually, he submitted thesis, and his exam is, uh, I think, in March 10 or so. So he'll be finishing up. And as part of his PhD dissertation, he prepared a very comprehensive review of the air pollution models for various applications. So some of these models are actually developed by private companies, but the codes are available, and so he made a comparative study of some how many 96 air pollution models, different well, computational fluid dynamics model, very complex, of course, simple Gaussian models, or some of the EPA recommended models, air mod, and those kinds of things. So he made a very comprehensive study of those, or review of those air pollution models, and it's a part of the EPA report that has been published as an EPA report, And out of 96, I think some 9 or 10, the models one can use for emergency response applications, for especially in urban areas. He kind of gave a little more extensive review of those. So one of the objectives is, of course, using emergency response models, which you cannot have very complicated CFD, computational fluid dynamics, but they have to be somewhat simpler. They can be used, quickly for emergency response purposes. So
model, basically.
yeah, so that's a very comprehensive. That's one of the chapter in his PhD dissertation. Another is, of course, he also analyzed the data. Uh, they called this study in Utah. Steve Hanna was involved in that too. That Jackrabbit 2016 Jackrabbit field study. The models of buildings. They had these containers, basically containers used as a models of buildings, and studying the dispersion of pollutants, both.
Well, in the past, all these field experiments, including the urban experiments data set, about 33 of them, including the jackrabbits and so on and so forth. I have all that data set at GMU. And I store them, I have them, I archive them. So
actually, this student, is Michael Pirhala, his name. He got those data, and he made use of those. Not only he used those data in simulating some of those flow and dispersion around buildings in the wind tunnel. So he also studied models of the same types of buildings in the wind tunnel, and compared with the field experiment and numerical models, So that's part of his thesis also.
So where do you see the future actually?
Future, I think we have probably plenty of numerical and computational, some of the analytical models too, simple box type models, depending on what kind of application you're using. So I think the model use these models have been quite useful. APA has recommended for various purposes, for urban use, rural use, for complex terrain, and so on. I think we have probably plenty of models. You just have to make select what might be useful for you.
Well, yeah. Any one of these models, as you very well know, it just gives you a single realization out of many. So you have some sort of, the probabilistic distribution within. It lies in that. And lastly, I just wanted to get your opinion on about the probabilistic calculations in terms of tackling the classic physics unsolved problem of atmospheric turbulence or turbulence, randomness of the motion. How do we really tackle that in the future? Probabilistic calculation or machine learning, for example. Nowadays, machine learning is making a big way, its way in this area.
Well, thing is, the best numerical model to study turbulence is, of course, direct numerical simulation. Direct numerical simulation where you don't have to parameterize any scale motions. Unfortunately, even now with the most powerful computers available, that is not possible to simulate the atmospheric boundary layer and turbulence, because the smallest scale is 1 millimeter, the dissipation scale, and the largest scale might be several kilometers, and just the number of grid points involved, to do the direct numerical simulation is just horrendous. You can't do that. So for certain smaller scale studies, like the ones we are studying in wind tunnel, you can do the direct numerical simulation too. But for others, you have to use some sort of closure, higher order closure or turbulence kinetic energy type closure and so on.
Very good. Probably the last question is, what do you tell to the next generation of students? First of all, would you still recommend people to choose a career in air quality, air pollution modeling, air pollution micrometeorology, or would you suggest other fields like computer sciences?
Well, it depends on, I know some of our students, he did their master's in air pollution, did the experiments in the winter and all that, but the best job they could get was using their computer science. They took computer science courses too. Sometimes they do the minor in computer science. So several of my students, they did not go into the actual field of air pollution or meteorology, but they ended up using their computer science knowledge for various purposes. So I think it depends on what kind of job you're looking for. Some got job in these areas too, certainly, especially PhD students. Once you do PhD, you like to stay in that area, do teaching and research in that area.
Yeah, money talks.
Money, yeah. For computer science, sometimes at master's level, I think computer science probably pays more than the air pollution meteorology or boundary layer meteorology.
I see. So any other comment, Zafer?
Oh, no, except that, it's good to see you, Paul. It was wonderful to see you again.
Well, nice to see you. You're looking good, Gifford. Yeah, great.
For your information, I'm using your books in my courses. So meteorology and other air pollution, meteorology, and the dispersion, air pollution and dispersion.
Okay, thank you.
Well, good to see you. Thank you so much.
Good to see you. Very good to see you. Yeah.
Very good. Well, thank you, Dr. Arya, for your time and your memories that I found really interesting. And if you have, if the viewers of this video have any comment or questions, of course, they can contact us. Thank you very much for the attention.
Okay, well, thank you.